Hi, great that you tuned in again for this water treatment lecture. My name is Doris van Halem and I'm an assistant professor at Delft University of Technology. In this lecture, I will introduce you to the most important parameters for drinking water chemistry. I will go through some basic water quality calculations, which are crucial for later design of water treatment plants. If you have a background in chemical engineering or something alike, this lecture may be relatively easy for you. However, if you don't have a background in chemistry, for example, like our civil engineering students, this course will give you a quick recap of the core chemical calculations needed for the design of water treatment processes. We will focus on 5 different topics. First, ion balance, then pH, carbonic acid equilibrium, saturation index, and hardness. Before we get started, I recommend that you download the periodic table, for example, from the course platform. We will need it for many of our calculations during the course. Let's get started with the ion balance of a water sample. The ion balance is based on the principle of electrical neutrality, meaning that the equivalent concentration of positively charged ions, the cations, is equal to the equivalent concentration of negatively charged ions, the anions. Major ions, such as sodium and chloride, usually represent most of the dissolved ions in water. So, the sum in milliequivalents of major cations and anions should be nearly equal. This relatively simple calculation will help you to check if water quality analysis were performed correctly by a laboratory, and to assure that you included all relevant major ions in your water sample analysis. This formula summarizes the ion balance, with the sum of cations on one side and the sum of anions on the other side. The milliequivalents can be calculated with the concentration in your water sample, the molar mass, and the valence of the ion. Well, let's practice with an exercise. This slide depicts the water composition of a sample. However, the sulfate analysis failed. Assuming that the major ions have all been measured, can you calculate what the sulfate concentration in this water is? You can take the time to calculate this for yourself now by pausing this video. Restart it again when you're ready to hear the answer. First, you make a table with the concentration, molar mass and valence of all anions and cations. For example, in a spreadsheet. For sodium, this is depicted in the slide. Then calculate the valence concentration in milliequivalents per liter for all cations. This adds up to a total valence concentration of 6.14 milliequivalents per liter. Now, based on the principle of electrical neutrality, also the anion should add up to 6.14. When subtracting the valence concentration of the other anions, chloride, bicarbonate and nitrate, you end up with a valence concentration of 1.6 for sulfate. This equals 76.8 milligrams per liter. Well, one of the most important chemical properties of water is that it can be both an acid and a base. Because water ionizes into H+ ions and OH- ions. The ionization is an equilibrium reaction for which an equilibrium constant K can be determined. For a neutral solution, H+ equals OH- equals 0.0001 millimoles per liter. The concentration of hydrogen ions is usually denoted as the negative logarithm of pH, the negative logarithm pH. A neutral solution has a pH of 7.0 at a temperature of 25 degrees Celsius. A lower pH, meaning a higher concentration of hydrogen ions, indicates an acid solution, and water with a pH above 7 is a base. The most important acid-base reaction in water is related to the dissociation of carbon dioxide. This reaction takes a few seconds to complete. In practice, carbonic acid and carbon dioxide are considered identical and used as equivalents. The dissociation continues from carbonic acid to bicarbonate, as depicted in the slide. From these equilibrium formulas, it can be calculated which ionic forms of carbon dioxide are present at a certain pH value. For this purpose, it is convenient to rewrite the formulas in the pK form. pK equals the pH if the concentrations between brackets are equal, because log 1 equals 0. This graph shows the relationship between pH and different CO2-related species. In the low pH ranges, carbon dioxide contributes for 100% to the carbon in the water, while in the higher pH ranges, 100% consists of carbonate. Around neutral pH, a combination of carbon dioxide and bicarbonate is present in the water. The exact amount of carbonic acid or bicarbonate can be determined with titration methods. Well, this must have given you a quick introduction to acid-base reactions in water, which we will return later in the lectures about aeration and softening. Let's get active again with a few exercises. First, we will calculate the pH in 1 liter of demineralized water if 4.4 grams of carbon dioxide is added. Again, feel free to pause this video to take your time for calculation. In the next slide, I will explain the calculation step by step. First, calculate how much carbon dioxide was added to the water in mole per liter. Then use the equation of K1 to calculate how much carbon dioxide dissociates. In this exercise, 0.21 millimoles per liter carbon dioxide dissociates. The pH equals to the minus log of H plus concentration and is therefore 3.68. But what happens to the pH if 1 millimole per liter bicarbonate is dosed to the water? Well, for this calculation, you can use the equation of pH that equals pK1 minus log of carbonic acid divided by bicarbonate. The carbonic acid or carbon dioxide concentration is 100 minus 0.21 equals 99.79 millimoles per liter. The bicarbonate concentration is 0.21 plus 1 equals 1.21 millimoles per liter. And with a pK of with a pK1 of 6.35, this leaves a pH of 4.43. Well, I hope these exercises have shown you how the pH with acid-base equilibrium reactions can be calculated. The next topic in this lecture is the calcium carbonate equilibrium. In general, calcium carbonate is difficult to dissolve in water. From a chemical perspective, this is a precipitation reaction. But in natural water, also acid-base reactions with carbonic acid are involved. From the solubility constant, Ks, it is clear that the more carbonate is removed from the water, for example by dosing an acid, the more calcium carbonate can dissolve into the water. In nature, calcium enters the water because the calcium carbonate in the soil reacts with the carbon dioxide in the water, which is produced through dissimilation processes in the subsurface. When all calcium in the water has originated from calcium carbonate and not, for example, calcium sulfate, it holds that calcium equals bicarbonate divided by 2. Therefore, a third power relationship between carbon dioxide and bicarbonate holds for this equilibrium. The graphic presentation of this is known as Tillmans diagram or Tillmans curve. The blue equilibrium line separates the aggressive water or calcium carbonate dissolving water above the line and the calcium carbonate precipitating water below the line. The curve is temperature dependent and will shift upwards at higher temperatures. This illustrates that when water in equilibrium is heated, for example in a water cooker, it may become calcium carbonate precipitating, causing scaling on the equipment. The pH of aggressive water can be increased by the removal of CO2, for example, by gas transfer, adding a base, or a reaction with calcium carbonate, for example, during marble filtration. For calcium carbonate equilibrium calculations, you will frequently need constants as depicted in this table. Before we start the exercise, I want to introduce one last term, namely the saturation index, or SI. The saturation index is the degree of over or undersaturation of calcium carbonate. SI equals pH minus pHs. pHs is the pH at which water is in equilibrium and can be calculated with the equilibrium constants and calcium and bicarbonate concentrations. Well, let's put this knowledge into practice. On this slide, the water composition of a groundwater sample is depicted. And the question for you is, calculate the saturation index. I advise that you pause this video until you have performed the calculation. Simply press restart when you want to continue. Well, I hope you started with the calculation of the pHs, where it is crucial to use the unit mole per liter for bicarbonate and for calcium. With the pHs of 7.32 and a water pH of 7.06, it can be calculated that the saturation index is minus 0.26. Have you figured out if this is calcium carbonate aggressive or if it is calcium carbonate precipitating? Yes, you're right. This water is calcium carbonate aggressive because the SI is below 0. A saturation index above 0 is calcium carbonate precipitating, and an SI below 0 will dissolve calcium carbonate. For drinking water, it is preferred to have water that is slightly precipitating to prevent dissolution of materials during distribution. Apart from the pH and the saturation index, also the hardness of water is of importance for scaling potential. Hardness is the sum of calcium and magnesium ions in water. This is typically expressed in millimoles per liter, but also the term German hardness is practiced. 1 degree German hardness equals 0.178 millimoles per liter. The last exercise of this lecture is to calculate the hardness of mineral water, as depicted in the table. Take the calcium concentration and magnesium concentration and calculate the concentration in millimoles per liter. For calcium, this equals to 0.125 millimoles per liter, and for magnesium to 0.041 millimoles per liter. In total, this amounts to a hardness of 0.17 millimoles per liter, or 0.93 degrees German hardness. The guidelines for tap water are not the same around the world, but now I will briefly summarize the guidelines as we know them in the Netherlands, the Dutch decree of water supply. These standards include that the hardness should be between 1 and 2.5 millimoles per liter, because if the hardness is too low, it may result in locally aggressive waters. And from a health perspective, it is also desirable to have some hardness in the water. If the hardness is too high, it may result in scaling once heated, as described with the Tillmans curve. So, the water should neither be aggressive nor scaling. The pH should therefore be within the range of 7 and 9.5, and the saturation index should not be lower than minus 0.2. We have come to the end of this lecture about basic water quality calculations. I thank you for watching and recommend to practice the homework exercises to get more familiar with these basic but crucial parameters. Thank you for watching.